Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So today we are going to discuss about the module Charge Transfer Devices, CCD, Charge Coupled Devices from the paper Semiconductor Materials and Devices. So students, the learning objectives of this module are: first, we will get to know the depletion region characteristics of MOS capacitor in a CCD. Second, we will learn about the arrangements of CCD. Third, we will also discuss or understand the charge storage and the transfer in a CCD. Lastly, we will study how these charge coupled devices are fabricated for use in practical applications. So students, let us start with a basic introduction about the module. Boyle and Smith invented the charge coupled devices, that is CCD, in 1970, and CCD can be contemplated as charge transfer devices. It is an array of closely spaced MOS devices where information can be stored in the form of charge packets in the potential wells created in the semiconductor by applying voltages at the gate of an array of MOS devices. So CCD can be considered as an integrated version of MOS bucket brigade device BBD, having wide range of applications due to low power consumption and high packing density. Now CCDs, they have been classified as first surface channel CCD, that is SCCD, second buried channel CCD, BCCD, third is peristaltic CCD or PCCD, fourth is profiled peristaltic CCD or PPCCD. Now, before studying the operation of CCD, it is important to study the transient characteristics of MOS capacitor operating in deep depletion region. So the representation of information in a CCD is different from that of the transistors, where instead of charges, currents and voltages are used. Characteristics or transient of MOS capacitor in deep depletion regime. So students, consider a MOS capacitor utilizing a p-type silicon substrate. That is, a positive voltage greater than the threshold voltage is applied on the gate terminal. Vg is greater than Vt of MOS. So after the application of the voltage, the device goes into the deep depletion region and the energy band diagram corresponding to the MOS capacitor in deep depletion regime is shown in this figure. So the energy band diagram of MOS capacitor in deep depletion region has already been explained in the MOS capacitor module, showing the formation of potential well at the semiconductor interface. So as evident from this figure, The formation of inversion layer is not there due to the absence of minority carriers immediately. Thus, the surface potential psi s naught increases as the large fraction of applied voltage appears across the semiconductor. As the time elapsed, electron-hole pairs are generated thermally in the deep depletion region. Electrons they start diffusing to the Si-SiO2 interface and hence forming an inversion layer. This time interval between the initial creation of deep depletion region and the formation of inversion layer is called as a thermal relaxation time. So depending upon the fabrication process, the thermal relaxation time can vary from seconds to some minutes. Also, thermal relaxation time depends on the flat band voltage, gate voltage, and density of generation of recombination centers at the Si-SiO2 interface. Information is stored in the form of charge, has to be transferred well before the thermal relaxation time, that is during deep depletion condition in the potential well as shown in this figure. So the injection of information signal charge carriers, that is Q info, in the semiconductor near the oxide interface just after the application of gate voltage. Now it is evident from this figure that there is an accumulation of signal charges in the potential well and resulting in a decrease in the surface potential to psi s. Surface potential. The surface potential, that is, if we want to examine the surface potential variation on the injection of information signal charge carriers, the relaxation between the surface potential psi s and the Q info has been derived. The surface potential psi s and the gate voltage Vg for a non-ideal MOS capacitor are related as Vg minus VFB is equal to V0 plus psi s, that is equal to minus Qs by C oxide plus psi s, where psi s is equal to QNaW square by 2 epsilon s and Qs represents the uncompensated acceptor ions in the depletion region of p-type semiconductor. C oxide is the capacitance of thickness D oxide and W is the width of depletion region. When no signal charge is injected, Qs is equal to QNaW. However, when Q info is injected, then Qs becomes Qs is equal to minus QNaW minus Q info. So now substituting the value of Qs from equation 2, that is the equation of psi s, into the first equation, Vg minus VFB is equal to QNaW by C oxide plus Q info by C oxide plus psi s. Now substituting for W from the relation of phi s in the above equation and solving, we get psi s is equal to Vg prime plus V naught minus bracket 2Vg prime V naught plus V naught square to the power half, where Vg prime is equal to Vg minus VFD minus Q info by C oxide. Now here V naught is Q Na epsilon S by C oxide the square. So the above equations depicts that for a constant value of gate voltage, the surface potential decreases linearly with the signal charge. Now let us discuss the principle of operation. The basic structure of CCD includes a p-type silicon substrate whose top surface is covered with the SiO2 layer as shown in this figure. Now an array of metal electrodes, or we can say the gates, they are deposited on the surface of oxide layers, each of which forms a MOS capacitor. These capacitors can be biased in deep depletion region, forming a potential well. So the depth of the potential well is a function of the applied voltage at the gate and becomes more at higher bias. So the information signal charge could be transferred from one potential well to the other by applying a higher voltage at the respective gate. Now let us discuss how a charge is stored in a CCD, that is the storage of charge. So here the voltage at the middle electrode is significantly greater than the voltage at its neighboring electrodes. So thus the electrons, they are introduced, they will get collected in the potential well as shown in this figure, formed at the center electrode and get confined in this well. So the charge would be stored in the well until the time is less than the thermal relaxation time. So students, let us now discuss the transfer of charge. This figure is depicting the charge transfer of the process. At time t equal to t naught, the applied potential at the right electrode is increased to V3, that is V3 is greater than V2, or we can say that Vc is greater than Vb. So the higher potential well results in deeper potential well, and hence charge, or we can say the information, could transfer from the potential well under the second electrode B to the potential well under the electrode C. So we can say from 2 to 3. Till now, the basic concepts of charge storage and charge transfer have been discussed in a CCD. So now the charge transfer can be realized practically using a linear array of three-phase CCD. Three-phase CCD. The basic schematic of three-phase CCD is shown in this figure. The electrodes are connected in the groups of 3 and a three-phase periodic waveform called as clock voltage is used for operation. Now the next figure explains a charge transfer process in a three-phase CCD along a linear array. Now the figure on the right hand side depicts the clock voltage waveform for three-phase operation. So now students, the timing diagram is shown in this figure and it is divided into three waveforms corresponding to three phases. The waveforms are identical for each phase but shifted sequentially by a time interval of t/3 with respect to each other. The voltage applied at any electrode is either at V1 or at V2, or it is changing linearly from V1 to V2 during a sub-interval of t/3. Now when these voltages phi A, phi B, phi C, they are applied to three-phase CCD, the charge, or we can say the information, starts transferring from one potential well to another sequentially. So let us now discuss the basic process in this. At time t equal to 0, the charges are present under the electrode A1 at voltage phi A with the value V2, and there is no charge present under the B electrode as they are at a voltage phi B with the value V1 for the time interval t/3. Also, there is no charge present under the C electrode as phi C has completed its fall to V1. So during the time interval from 0 to t/3, the voltage phi A decreases to V1 while phi B remains at V2, and the charge gets transferred from the potential well under the electrode A1 to the potential well under the electrode B1. This transfer process is completed at time t equal to small t equal to capital T/3. Similarly, at time t equal to 2t/3, the charge gets transferred to the potential well under the electrode C1. Finally, at the full time period of the clock wave capital T, the charge has been transferred to the potential well under the electrode A2. Thus, along a linear array, the charge has been propagated. So, there is a little loss of charge during the transfer when the time is small as compared to the thermal relaxation time, and the information is transferred from the input to the output of the device. For a N-type silicon substrate, the operation is similar except the voltages V1 and V2 becomes negative. So students, let us now discuss the fabrication of CCDs. CCDs, they are fabricated on silicon wafers and are being processed in a series of complex photolithographic steps involving etching, ion implantation, thin film deposition, metallization and passivation for different various functions within the device. So the substrate of silicon is electrically doped to form p-type silicon. Now various dies are fabricated on each wafer and are tested and packaged into a ceramic or polymer casing with a glass or quartz window through which light can pass to illuminate the photodiode array on the CCD surface. Now CCDs can be fabricated as surface channel CCDs, that is SCCDs, and buried channel CCDs or BCCDs. Surface channel CCDs. A nearly intrinsic polysilicon layer is used to cover the SiO2 layer. Then the polysilicon is doped heavily at a desired region after putting a mask on that region which is not desired. So the charge is stored and moved in a potential well at the silicon surface under SiO2, and hence this device is known as surface channel CCD or SCCD. In a SCCD, the surface potential should have a smooth variation across the boundaries of a semiconductor and oxide between the electrodes. This condition is fulfilled if the capacitors close together so that their depletion regions overlap. In a single metal gate structure, the spacing between the gate electrodes is 2 micron for a SiO2 thickness of 1000 angstrom. This small gap cannot be obtained by the photolithographic process. The doped polysilicon structure is an alternative to the single metal gate 3-phase CCD as shown in this figure. Buried channel CCDs. So this is the next type of CCD. The effect of traps is eliminated if the channel is moved some distance away from the interface. This condition is achieved in a buried channel CCD or BCCD as shown in this figure. So here the N-type layer is produced on the top of the lightly doped P-type silicon substrate by ion implantation. Then the oxidation of the wafer is done and N+ diffusion is performed for input and output diodes through the windows etched in the oxide. Then on N+ regions, ohmic contacts are made and the layer is covered with a series of metal electrodes. So the operation of BCCD can be understood as: consider a large positive voltage is applied to the input and the output through N layer while the gate is held at ground potential. Reverse biasing the substrate of the PN junction widens the depletion region of the junction on both the sides, N and P regions. Since the gate is also biased negative with respect to N region, below the metal electrodes, a field-induced depletion region is formed. With increase in the reverse biasing, the two depletion regions would meet at a distance away from the interface, thus potential acquiring the maximum value. Therefore, the charge injected will be attracted in the potential and remain there, and this charge can be transferred to the other electrode by the application of a suitable clock pulse. So basically, students, the difference between the surface and buried CCD is that the electrons forming the charge packet in a CCD are minority carriers and forms a thin inversion layer near the interface, while in the BCCD, the stored charge is of majority carriers that replace some of the electrons removed during depletion region formation. So students, let us summarize what we have learned in this module. First, the MOS capacitors biased in deep depletion region. They are the building blocks of charge coupled devices were discussed. Second, the thermal relaxation time is the interval between the initial creation of deep depletion region and the formation of inversion layer. So in a CCD, the information is in the form of charge. It has to be transferred well before the thermal relaxation time. Next, the information, that is the signal charge carrier's Q info. It is injected into the semiconductor near the oxide interface just after the application of gate voltage, where they will get accumulated in a potential well. Now we also discussed about the three-phase CCD, which consists of a linear array of MOS capacitors where the electrodes are connected in a group of three-phase periodic waveform. Lastly, the charge carriers at the input can be generated through avalanche injection or optical injection, and the output arrangement of a CCD consisting of a reverse biased PN junction diode were discussed. Thank you.